So, hello everyone. I'm going to talk about giant planets and trying to do give you a picture about how to derive the bulk composition of the planet and what the results are for a large sample. So let me start with this classical mass radius diagram for which you see all the confirmed transiting exoplanets. There are about 1,000 of them considered as confirmed and about 400 with defined mass, or at least an estimate on the mass. So you see on this diagram that the temperature could go as low as 200 K up to more than 2,000 K. And I'm interested in the giant planets regime, so that means it's between 0.1 and 10 Jupiter masses. And in this regime, you can see that most of the planets are around 1 Jupiter radius, and a few of them on the less heavy side span a range much higher in radius. So in order to infer the bulk composition of the planet, Isabelle gave a wonderful talk, so you know a lot now. We need to use a model that will basically solve, so this code is called CEPAM. It is solving actually the quasi-static equilibrium equations. And so we are assuming that the planet is made of a fluid envelope of helium and hydrogen of solar composition, also in heavy elements in that. So for this problem, we have boundary conditions at the center. Of course, there is the mass must be equal to 0 and the luminosity must be equal to 0, and the boundary condition at the top of the atmosphere. And this boundary condition, we are using a Guillot 2010 model, for which there is a direct link between the equilibrium temperature of the planet to the temperature of the atmosphere. So, of course, most of the planets that we observe are in fact orbiting stars, and those are the planets that we are interested in. So planetary parameters really depend on that of the stars. And that's really important because the uncertainties that we get on the observations, namely the mass, the radius, and the equilibrium temperature, really most of the part of that come from the uncertainties in the stellar parameters. So we are using usually some tools to try to combine the modeling of the star and that of the planet. So I write my own, which is called SET. And the nice thing about this is that instead of modeling first the star and then after the planet, you do all the same at the same time. And you can include different models, so you get estimate on the intrinsic errors. And you have robust statistics using MSCMC, so you propagate errors correctly, et cetera, et cetera. And this is designed really to do quick and robust modeling of both stars and planets that is well suited for large samples. So this is exactly the starting point. We are going from the case-by-case study, and I will review just a few of them. Basically, there are three interesting categories in the giant planets. The ones that are inflated, the ones that have a massive core, and the ones that are young. Among the inflated ones, that means that a standard model with just helium, hydrogen envelope, no core, of the given mass and equilibrium temperature as observed, is not able to reproduce the observed radius. So you can see well, you cannot see very well, maybe. So the black line here is a standard model, and the red area basically is a constraint on the base constraint on the planetary radius. So we come too short to explain this radius. So for these categories of planets, we need some kind of inflation mechanism that will puff up the planet and match the observed radius. The second category is a massive core category planets. So for these planets, actually the standard model for on this plot, the top line, is giving a radius at the given age too large as compared to the observed one. So for these planets, it's relatively easier, in fact, because you just need to as Isabel explained, to put some heavy elements in the planet, whether in the core or whether in the envelope, to make it smaller at a given time. And then again, well, there is a CoRoT-20, which are really extreme, but again, there are maybe some new studies that show that maybe the planet has a larger radius. So if there is a larger radius, well, that will decrease by a lot the amount of heavy elements that are needed for that. And finally, there are the young planets. And the two interesting examples of these are CoRoT2 and CoRoT18. And so these planets are interesting because usually they are kind of problematic. CoRoT2 has a very large radius for a quite heavy mass. So it's very hard to explain. You need a lot of dissipation, unphysical. And CoRoT18, which is similar to CoRoT2, actually have some different kind of problems. So well, these are the three interesting categories that I found in the giant planets. But of course, there are some planets that has been observed that are not that tricky. For instance, one of the key milestones of the exoplanets ones are CoRoT9. CoRoT9 is the most similar Jupiter-like planets. It's about the same mass, about the same equilibrium temperature. So we should expect from this planet to have like roughly the same bulk composition as a Jupiter, of course. And that is the case, actually. So both the model on the right shows that the planet should have like between 0 and 20 Earth masses, which is similar to Jupiter. And of course, there are some planets where you cannot really distinguish between standard models without dissipation that give you a smaller core mass than models with dissipation in dashed line there, where you need more heavy elements to explain the radius. So we are starting to shift between the case-by-case study to an ensemble study. So we are taking into account a large number of planets now. And let me start by defining the radius anomaly, which is equal to the difference between the observed radius and the radius of a theoretical model standard with no core of the same mass and same equilibrium temperature. So this radius anomaly should be equal to 0 if if the model is playing perfectly the observation. If it's above 0, that means the planet is inflated. So you need some kind of inflation mechanism to explain that. If it's below 0, then you need some kind of heavy element inside the planet to explain the observation. So one of the variations that has been observed by Laughlin in 2011 is the correlation of this radius anomaly with the equilibrium temperature. And you clearly see that for a large stellar insolation flux, the higher number of planets get inflated. So the 0 line is here, and when the equilibrium temperature is increasing, the proportion of inflated planets is also increasing. And he found this relation. So in order to assess this radius anomaly for a large number, we needed to build a grid of planetary models. So we did that with CEPAM, with temperature ranging from 200 to 2,200 K, masses from 0.1 to 10 Jupiter masses. Heavy element assuming the core, that's simplistic. As Isabel said, that will probably overestimate the amount of heavy element that we are finding, but well, that should do it for now. And we are assuming that there is between 0 and 50% of the total mass of heavy elements. We are also exploring different dissipation proportion of the stellar incoming flux from 0 to 50%. And of course, we are doing the full evolution, so between 0 and 40 gigayears. So these are the preliminary results. We modeled 249 planets. And luckily, we do find again this correlation between the radius anomaly here on the left together with the equilibrium temperature. So you clearly see this correlation. I like to point out that there are few planets here that tends to not follow the correlations, and they almost all are TTVs. I will come back a bit later on that. So on this diagram, you see that there is 60% of the planet that has positive radius anomaly, which is a huge amount. So indeed, there is a lot of planets that are inflated. And this planet requires some kind of inflation mechanisms to explain the radius. Isabelle did a wonderful job to sum up all the possibilities. So I just remind you there are kind of three categories. The ones that are dissipating the stellar flux, so kinetic heating, ohmic dissipation. There are tidal dissipation. And then again, there are more physics fine-tuning mechanisms, increasing the opacities or having double diffusive convection. So all these should be the mechanisms that we are thinking of to explain the inflated planets. Another interesting correlation that has been found previously is the correlation between the metallicity of the planet to that of the star. And so on the right here, you see the core mass of a number of planets as a function of the metallicity of the star. And these planets are planets with equilibrium temperature quite large, around or above 1000 K. And you see clearly a correlation here between those two metallicities. Again, below is a plot for some planets with low equilibrium temperature. And again, you see this correlation. The scale is not the same, so that's why this is the line here and the curve. So the first thing we did is to compare what we obtained for the large sample with regard to that previous studies. And in red are our results, and the blue are the results that I've shown in the previous plot, and you clearly see that we find again this correlation. However, if we take into account all the planets, this correlation tends to disappear. But we have to be careful, because there are a lot of things going on. So first of all, let's consider this plot. This is the star metallicity, as previously, and this is heavy element mass fraction in the core. And the colors correspond to different kind of servers. The blue ones, especially, are Kepler planets. And you see that this unphysical result of Z value of above 1 is meaning that there is no model at all in the grid that could explain such a small radius for those planets. So let me try to separate all the data. Now I'm considering just the planets with low mass, below 1 Jupiter mass. And you see that all the top planets that we've seen previously are all low mass planets. And in fact, they are all almost Kepler. And Kepler, in fact, have been finding a lot of planets around the poor metallic stars, and so maybe there is a bias there. But again, we don't see the correlations that we have found previously. However, if we consider only the heavy mass planet, so above 1 or 1.5 Jupiter masses, we see again this correlation with all the planets. So that's kind of tricky to disentangle these results from some kind of bias that we could have in the sample. So the perspective is really the data mining. Here I show you the plot for all the three main database of exoplanets: Exoplanet Archive, exoplanet.org, and exoplanet.eu. All the points should be on the same spot because that's the same thing. It's not the case. And again, if you see on the lower left of the panel, you see that most of the probability planets are in fact TTVs. So I would like to say that TTVs to me looks a bit tricky to explain. So the second perspective that we have to do is to update the physics of the grid we have. So we'll update the atmospheric model by using the one presented by Vivien yesterday. And we also plan to include the new equation of states as explained by Isabelle. And of course, we have to do that in a more robust way. So we want to model the star and the planet at the same time. And this still has to be done. And we have to really take care of which data we will pick. So we will not trust any of the database, and we have to go at each articles and see what are the things. So the future is quite bright because PLATO, Gaia, TESS, a lot of projects that go on that will probably bring like more than 1,000 giant transiting exoplanets with mass determination and radius determination. So that will increase a lot the sample and allow us to build better statistics. That still remains to do. So thank you for your attention.
Thank you, Mathieu. Questions? Yes, Suzanne.
I was wondering, when you were showing the correlations between radius axis and effective or equilibrium temperature, surely you'd expect it to depend on the planet mass as well, wouldn't you?
So you mean which correlation?
The radius axis,
yes,
compared to the equilibrium temperature of the planet. So just before that, for example, this one. You would expect a dependence on the mass of the planet as well, wouldn't you? Because it's much easier to puff up a low-mass planet.
Yes, kind of. Yes, kind of.
So I was just wondering if you've checked for that, because it's something I looked at. 5 years ago it was definitely there, but I don't know if it still is there.
So it's very preliminary result. Actually, it's like 2 or 3 days recent. So there is a lot of statistics that needs to be done yet to make sure that everything has been done properly and test what is the correlations, the trends, and the mass dependency, etc., etc. So yeah, that's definitely a point that we have to look into.
Maybe if I can ask a question which is more related to this plot, how do you explain the spread of the points? Because there is a correlation there. I agree with you, but with a large dispersion, do you have any hints to explain?
No, not yet. Well, there is. So this is just a 2D plane. So you have to take into account, in fact, the mass. So that could explain part of the spread. You have to take into account also that maybe so just a small number of the planets are in multiple systems. So there is a kind of competition also in there. There are different around different stars. So maybe that should affect also the. Well, there is a lot of things to look into, but yeah, definitely.
Questions? Yes.
I can see how you can explain inflated planets, but what about the deflated ones?
The one that requires a large core mass, is that what you mean?
The ones with a negative radius anomaly.
Yes, that's the one that needs a heavy element inside to explain the radius. Some of them it's relatively easy, like CoRoT10. There is a large amount of heavy element in the core, but you can explain that by just putting heavy elements. And some of them, like CoRoT20, are just like incredible, like not physical.
TTVs were suspected to produce lower masses than radial velocity planets. And now what you say that the TTV planets include heavy metals.
Sorry, I said
TTVs, by the paper by Weiss et al., were suggested to produce statistically lower masses than radial
Yes,
velocity
it's been shown by Alexander also yesterday. Yes.
And what you suggest in this figure is that TTVs produce lower radii, so more metal content. So these two things appear to me a little bit contradicting.
Well, so the problem I'm pointing out here with the TTV is that those planets, basically, here you see here, there is no model at all that could explain them. Whatever the physics you put into the model. So maybe there is a trend that TTVs shows smaller radius, but anyway, I mean, if it's not explainable and physical, then it's wrong. So I don't know what I know that some of the points here in the database are not correctly are not correct, in fact, because I know that there is some larger error bars in the mass that are not shown in the database, but I know that the papers pointed out that there are larger error bars. So maybe all these points with a careful veiling and data mining will maybe disappear. Let's see.
Other questions? Yes, Sasha.
Yes, in this model, normally you assume, I remember Isabelle saying that homogeneous convection or adiabatic convection. So do you use mixing length theory to deal with convection in your planet?
Yes.
If so, what value of the alpha parameter?
1.5.
Yes, and so why are you using this value, and how sensitive are your models? I guess you are varying this parameter also, or all the models you have computed were with a fixed alpha mixing length?
It's all fixed, and actually, so CEPAM is coming from a stellar evolution called CESAM.
I know CEPAM very well.
Yeah, okay, so that, yeah, actually we keep fixed this alpha value.
So I don't know how this has been calibrated, and when you compute Jupiter, do you compute with alpha 1.5, the model that Tristan has published?
Yes.
But do we have an idea, because I know Rainer has also looked at that for stars, and we know the alpha, when you start doing 3D models of convection, you find that the alpha is perhaps not a very well-constrained quantity. So if you were releasing this constraint, what will happen?
Well, so that I never tested it. Maybe Tristan did, so he should answer that. But the thing is that I think there are some larger source of uncertainty in the model, like equation of states, opacities, etc., etc. So I don't think this alpha value will be much of a problem in this context, but maybe Tristan can answer.
Yes, almost nothing would change because for these planets you're very close to adiabatic convection. The intrinsic flux to be transported is very small compared to the internal energy, so it's not a big parameter. So we fix it to 1.5, but we would use. Yes, on stellar models, it's definitely different. I have just a small comment on the TTV planets, that we have to be cautious that those are small size planets.
Yes.
So for which our models are assuming just a core and hydrogen envelope is probably not correct there. So
we have to be more careful, I do agree.
Okay, very last question, and then I've been waived that we will have to finish the session.
This is just a comment. When you showed the first time the metallicity correlation, the other way around.
No, metallicity.
There, upper right. Sorry, but I think that's just wishful thinking. I mean, that's not convincing that there isn't any correlation at all. I mean, that line in the upper right.
So, I do agree. Well, no, it's been shown statistically that it's relevant. However, if you remove like, well, 3-4 points, so that's why it's important to have a large sample and be careful of the data mining and see if there is or not. There is no clear answer for now.
Thank you, Mathieu, and thank you to all the speakers.